understand.
Yeah.
Good. I have a question. In ordinary classical mechanics, on phase space, is there a metric on phase space?
There's a form.
There's a symplectic two form. Symplectic. It's
Okay.
symplectic forms, not necessarily.
Yeah. Why is there no metric?
Well, you can have characteristics clashing.
Why not a metric? dp squared plus dq squared or something? I'll tell you, the answer is that it's not invariant under canonical transformations. Canonical transformations are the basic symmetry structure of classical mechanics.
Mm-hmm.
But there is one metric. It's a stupid metric for sure, which is invariant. And it's just a metric which says the distance between any point and itself is 0, and any point and any other point is 1,
Okay.
or pi over 2. That's equivalent. Yeah, that is a metric. There's a quantum mechanical analog of it, and we'll talk about it in a minute. I'm going to stop.
Does that like
It's
involve
more-
the digital topology on the sets?
Well, you're reading too much into my remark. Yeah. All right, but the question that I want to begin with, we're going to talk about complexity, and for the rest of the quarter we'll talk about complexity. I want to begin with the question, and I'm sure that some of you know something about this, but still I want to start with it. Is there a good notion of the distance between quantum states? And what is it good for? And is it good for all the things that we might want a good notion of distance between quantum states? So, yeah, there's a standard definition of quantum states, of distance between quantum states. It's the inner product metric. I call it the inner product metric. Other people call it the Fubini
Study, is it Tensler?
Fubini study metric. Study. Study doesn't mean that he studied a lot. This was a guy named study of student. Okay, distance between quantum states. All right, so the usual definition is that the cosine of the distance between states, and when I say states, I mean normalized states, and the states of unit norm in the Hilbert space of whatever we're talking about. Distance between A and B is the cosine of it is just the cosine of the is just the absolute value of the inner product between A and B. If A and B are the same state, then the distance is 0. If A and B are orthogonal, the distance is pi over 2. And with this definition, the maximum distance is pi over 2.
Yeah, but hold on. Shouldn't this be an infinitesimal? Is this really?
Yes, except the space of states is nice and homogeneous. So in fact, this would be the distance in the sense of geodesic distance between minimal geodesic distance. Yeah. So right. So you can just define it this way.
Okay.
Okay, so that's the standard inner product distance between states, and it has all kinds of uses, but it is not a good measure of what we might call the dissimilarity of states. Oh, incidentally, this is the analog of the stupid metric that I told you about classical physics. It never gets bigger than pi over 2. And it's pi over 2 when things become orthogonal. Well, in classical physics, all states are orthogonal. Any pair of states are orthogonal, meaning to say any pair of states are distinguishable. And this is the analog of, if you like, the stupid metric. All right, let me give you an example of when I say that it is not good for measuring the dissimilarity of states. I'll give you an example. Take a state A, and I'm thinking about now qubit states. Some large number of qubits, 0, 0, 0, 0, 0, dot, 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 0. And compare that with B, which is 0, 0, 0, 0, 0, dot, 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 1. These two states are as far apart as possible. They're orthogonal. they're orthogonal. It is not very difficult to go from one to another. You just flip one bit. So it's pretty easy to go from one to another, to make a transition. It's also easy to create a superposition of such states. You just forget about all the others, and you do whatever it would be to take a 1-qubit state and make a superposition, rotate it in a magnetic field or whatever. And it's also very easy to measure, if you had such a superposition, the interference angle between them. So that's easy. Now, we could flip over a few more spins. Here, or let's say here versus here. And let's say, this state is getting to be more different. B is getting to be more different from A than the original states. It's a little bit harder to make a transition. You have to flip over not 1 qubit, but some larger number of qubits. The states are becoming more dissimilar, but still, they're no further apart than this pi over 2. Okay, you can get even stranger things. If you were to take A and evolve it with a Hamiltonian, some typical, let's say, generic Hamiltonian, some Hamiltonian that we might call chaotic. Hold B fixed, for example, or hold, no, let's not hold B fixed. Let's take both, let's involve both of them, e to the minus I h t B. These, in some sense, get very different from each other. They get enormously different from each other in the sense that it gets harder and harder to superpose them. It gets harder and harder to measure the interference between them. And it's harder and harder to make transitions between them. If it's a chaotic system, in classical physics, let's come back to classical physics for a minute. If the system is chaotic, and you start with 2 neighboring states, you can think of these as neighboring, although I haven't told you in what metric. But think of them as more neighboring. What happens as they evolve? They evolve and go off in wildly different directions. And after a pretty long time, they become extremely different from each other. Different from each other in the sense that, well, just very different from each other classically. In the semi-classical physics, it might be very hard to make transitions between them. They become different from each other because of chaos. And we might expect the same kind of thing in quantum mechanics. You start with neighboring states, you evolve them for a long time, they do become very different from each other. Different in the sense that it becomes very hard to make transitions between them. Now, the question is, how do we quantify that?
Are you equivalent to say that I have to flip more bits on every?
It's much worse than that. There are all sorts of phases, but it's much worse than just having to know. Classically, it would just be a number of bits you have to flip. Right, that never gets too bad. I mean, if it was just classical automata, or classical cellular automata.
It's just the word, it's just the number of words.
But the maximum number of bits you would ever have to flip to go from here to here would be n. And there's a small potatoes here.
Okay.
We're talking about exponential things. Okay, so it's pretty clear that inner product distance is not particularly appropriate for describing the difference between states or the distinction between states in general. And the question is there another metric on the space of states which is better? Well, it kind of depends. In asking how hard it is to do something, it kind of depends on what you're allowed to do. If I ask how hard is it to walk from the North Pole, to get from the North Pole to the South Pole, if the rule is I'm allowed to go from any place to any other place instantaneously, it's not very hard. But if my rule is I have to walk with one foot in front of the other in front of the other, then there's a measure which is the number of steps I have to take. Okay? So we need to have an idea of what is allowable, what kind of operations are allowable, and there's no general statement about what's allowable, what's not allowable, but the usual idea is that what's allowable in a qubit system is to bound the number of qubits that a single operation can involve. So for example, let's start with 1 qubit operations. 1 qubit operations just means 1 qubit unitary operations on a qubit. Question, can you go from any state to any other state by 1 qubit operations? Okay. No, because you cannot go, for example, from an unentangled state to an entangled state. 1 qubit operations will not lead to entanglement. So 1 qubit operations would not be enough to take you from any state to any other state. How much do you need? Turns out all you need really is 1 and 2 qubit operations. At least if you just want to get within an epsilon distance of, we're going to ignore epsilons for the most part. Okay, so let me make a proposal. The proposal is you're allowed all 2 qubit gates. So you can go from any place to any other place with 2 qubits. Let's take that as a sort of fiducial definition of what you're allowed to do. Later on we can ask what would happen to the measure of distance if we allowed 3 qubit gates, 4 qubit gates. What we would not allow is n qubit gates. That would be like going from the North Pole to the South Pole instantly. And define in the following way, having picked our gate set, it's called a gate set, the allowable gate set, 1 qubit gates and 2 qubit gates, no more. As I said, we can generalize that later. And imagine a quantum circuit. A quantum circuit is just an evolution of a set of qubits. These are the world lines of the qubits, if you like. And gates simply are interactions, unitary interactions between pairs of qubits or single qubits. You can make single qubit gates out of 2 qubit gates, so we could restrict ourselves to 2 qubit gates. But you cannot make 2 qubit gates in general out of single qubit gates. So that would be, all right. Now, let's start with a state A and apply to it a circuit. A circuit means a product of gates. The gates don't have to be neighboring. There's no sense of neighboring. Just a sequence of gates and go to B. Let's look for circuits. Let's take A to B. What this means is your circuit is defined by a product of gates. This is Gn, Gn minus 1, dot, 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 all the way down to G1. And we're looking for circuits which will take you from B to A. Again, I emphasize in this business there are issues of epsilon, but I'm going to suppress them. And look at all possible circuits which can take you from A to B. Okay, all possible allowable products of gates which can take you from A to B. The definition of the complexity of the quantum computational complexity is within your allowed gate set, the minimum number of gates that it takes to go from B to A. So that's the definition of complexity. If my allowable gates, the canonical choice might just be all 2 qubit gates and 1 qubit gates, all possible 2 qubit gates. For a computer scientist, they might want to limit the gates to specific kinds of 2 qubit gates, ones which are easy to make in the laboratory. I know it's not important. That distinction is not very important. Okay. This is called the relative complexity of A and B. It's the relative complexity of the state A and B. And it is a measure if your physics is such that it's difficult to apply many qubit gates. For whatever reason, this is a measure of how hard it is to make a transition between A and B. By a theorem which is due to myself and Aronson, the theorems are always the same. I ask the question, he gives the proof. The theorem says that the relative complexity is also the minimal gate complexity to measure coherent phase between A and B. If you had a coherent superposition of A and B, and you want to do some kind of measurement that will detect the angle, that will be sensitive to the angle of the coherent superposition, then it is also the number of gates in your experiment basically has to be the same thing. So this is a measure of a number of things, this complexity. How easy is it to make a transition from one to another? How easy is it to measure the interference between two such states? And also how easy is it to create a superposition of the two states? That's a little bit different, but it is also a measure of that. So it is a measure, in that sense, between the distinction of states, between states. And now we come back to here, to these two states. How can you go from here to here? How can you go from here to here? You can go from here to here. Let's see, what do we have? We can think of one state and the two neighboring states as going off in some direction. This one goes off in some other direction in a space yet to be defined. And if we, roughly speaking, think of that evolution as a series of gates, and this one is a series of gates, we can always get from here to here by backtracking here. That means running the backtracking, incidentally, one thing. The allowable gate set is always such that if it contains a gate, it contains its inverse, it contains its Hermitian conjugate. Okay, let's assume that. So that means what that comes down to is saying that if the relative complexity of A and B is this thing, then the relative complexity of B and A is the same thing. You go from B to A by inverting this operator, has the same number of gates, and so the relative complexity of A and B is symmetric between A and B. All right, you can run back from here to here. Now, it takes one gate, in this particular case over here. Once you've run back to A, you can make a 1-qubit gate to go from here to here. And then you can run this way. So whatever the number of gates that it took to get here, presumably the longer the time here, typically the more gates that it will take. Whatever the longer the time, the more gates it will take to go from here to here by this particular route. Now this particular route may not be the shortest route. Okay? There may be shortcuts. There may be shortcuts, but usually not, or usually not very shortcuts, and we'll talk about that a little bit. If we ignore shortcuts, then the shortest way to get from here to here, before shortcuts, is to backtrack and go this way. And that means that the relative complexity for a chaotic system, as the time gets large, the relative complexity of these evolutions, although they started from two neighboring states, will get very large.
Shortcut would be like non-trivial topology in whatever the space is.
Something like that. Something like that, yeah. Not exactly, but something very close to that, yeah.
Or if the Hamiltonian were not chaotic.
Well,
Well, that,
yeah, then they're not split. Yeah, sure. Like
That's
they went like that.
Yeah, good. Okay, so we can also talk, incidentally, not of the relative complexity of two states. We can also talk about the complexity, the absolute complexity, if you like, of unitary operators. Instead of talking about the relation between two states, let's just talk about a circuit. A circuit means a product of gates, which computes or creates a unitary operator, a particular unitary operator. A unitary operator could be the time evolution of a system. Let's just given a unitary operator, what's the minimum number of gates that it takes to generate it in this form? That would be called the complexity of the unitary operator U. What's the complexity of the unit operator? Well, it doesn't take any gates to generate the unit operator. Of course, you could generate the unit operator in a stupid way. You could multiply a bunch of gates and then follow it by a bunch of inverse gates.
Yeah.
So the rule is not that the complexity is the number of gates that you use to generate the operator. It's the minimum number that you could have. Okay.
The identity operator always has to be in the gate set?
No, it's not in the gate set.
Yeah.
It's not in the gate set, but it is a unitary operator.
No, I know, I'm just
It
wondering.
could be in the gate set.
I'm just wondering, could I pick a really bad gate set where I have to multiply like 15 gates together to get the identity or something?
I mean,
You always
No,
have
no, there's always a
You always have
possibility of
G
no
inverse.
gates.
Yes, no, yeah, that's it, right,
No,
right,
the
right.
cheapest thing is no gates.
Right, because you have, you always have G inverse.
In fact, even if you include the identity, you never use it in the minimum length, so.
Right, sure, no, got it.
Perfect. Okay, so another way of talking about relative complexity of two states is just find the unitary of minimum complexity that connects those two states. So you look for all unitaries which connect A to B, that is not unique. There are many unitaries which will take A to B. Look for the unitary of minimum complexity that will connect A and B. That's another definition. I mean, it's identical. The content is identical to the definition in terms of number of gates that take A to B. It's obviously the same thing. Okay, so as I said, it's
I know you said that you don't want to worry about the business of epsilons here,
Yeah.
but is the statement that, you know, once I start taking epsilon small, I can define a different complexity for each value of epsilon, and that has a definite power scaling with epsilon, or
logarithmic.
logarithmic with epsilon? Okay.
Yeah. That's what we tend not to worry about. Okay.
Leonard, sorry.
Yeah.
Oh, what if you know measurements?
Say it again.
If you let measurements, does anything change?
What if you let measurements into the game? You can do that.
So how do you define this for non-pure states, I guess is the
Mhm.
question. You mean
No,
if
you
you have
weren't
mixed
asking
states?
about non-pure states, were you?
No.
Oh,
Just do some measurements and
Yeah.
project.
You could do that.
Projectives.
You could do that. It's not traditional to do that than what's usually called gate complexity.
But if it's still a pure
Yes,
state.
but does it change your? I mean, if you allow that, does it
It
change?
probably does. Probably changes it a lot. You can go from some wildly complex state to any state which is, all right, let me make a definition for you. We have a system of qubits. Those qubits, the identification of those as qubits picks a qubit basis. You can find other qubits in the same Hilbert space, but we pick. We pick a basis of qubit states, and then we also pick a basis within each qubit space. For example, the Z basis, the basis diagonal of sigma Z. That's a basis, for example, all states up, all states down, or all states 0, all states 1, but any combination 0, 1, 1, 0, 0, 0, 0. Those are a basis of states called the computational basis. We'll just call that the computational basis. I forgot why I mentioned that. What were we saying? I don't remember.
You can always measure on the computational basis and then get to this.
Oh, yeah,
Yeah, because it will
right,
project
you
down
can take
something.
any
This thing would be immensely complex.
terribly complex state, and then just measure it in the computational basis, and it will become a state which is no more complex, no relative complexity will be bigger than n. You can always go from one to the other.
Because it'll pick some,
Yeah,
or there won't be,
there's somebody
it
who-
should move
Well,
on.
the reason I was thinking about mixed states is one could really say measurements putting you in a mixed state.
Yeah.
So is there a definition of complexity for mixed states?
Well, you can think of a measurement as creating an
Average.
entanglement.
Yeah.
Is that what you mean?
So if you include the observer, sure.
Yeah.
But
But
sorry, that will let you to make non-complex states from complex state.
yeah.
But you want to do the opposite.
That's
You also
good.
want to do the
Okay, so
opposite.
that's an interesting question. Can measurements increase complexity?
I mean, if it's going to be reversible if you allow post-selection, but
Don't they increase complexity if you look at the full
Let me
system?
make a definition, another definition, which is sort of standard. The absolute complexity of a state, in order to define it, you need the notion of a reference state, which you call simple.
Yeah.
Okay. Simple states, usually by definition, are states which have no entanglement. you could pick an unentangled state. Here's your favorite unentangled state, and say that by definition, that's your simple state. And then the absolute complexity would be the relative complexity of the state relative to the simple state. So that's a notion of absolute complexity, and I don't remember why I said that either.
One thing that always gets me these complexity, that seems like to be the only viable definition, that you always have to have a reference state. I mean,
Well, yes,
yeah.
yes, yes.
So this is sort of like
yes.
defining potential energy. You don't care about the absolute potential.
But relative complexity doesn't require it.
Right, no, but I think relative complexity seems to be the thing that's defined. I mean, it's just like saying,
In the case of unitary operator complexity, you do have a distinguished unitary, namely just one.
okay.
And so in that sense, you don't, it's natural to think of the unit.
No, but I was thinking this in terms of like black hole thermodynamics or something like that. If I could think, I can make reference state, I can make it the input state, I can say all, like a photon.
Right, I mean, the input state
Yeah.
is generally a bunch of relatively unentangled
Right,
particles.
so that would always be my, I can always start with that.
That's right.
I mean,
So that's,
product states are kind of picked out, but once you pick what your qubits are, right?
say it again.
Product states are kind of, the set of product states is usually determined once you decide that you have these qubits.
Yeah.
And then the relative complexity between product states is going to be small.
Yeah, it'll never be bigger than n.
Yeah, so that's a natural choice and probably equivalent to.
You say n
more or
could be a
less.
big number, yes, n could be a big number, but by comparison with the one we're going to be talking about, it's a small number.
Is it known if I measure the complexity of like the Hamiltonian time evolution in this way by the number of gates, if I restrict to an energy window, can it change dramatically? Like a wide energy window, obviously, not like a
Let's
projector.
just say it again.
Like, okay, so let's say I take the time evolution,
Yeah.
which is minus IHT,
Yeah.
and for a fixed time,
Yeah.
and I compute the complexity by this definition of
Yeah.
complexity for
Yeah.
unitary. And then I restrict to a large energy window, that contains some finite fraction of the states.
Yeah.
Uh,
But you're looking at pure states. You're looking at pure states.
Sure.
Okay.
Well, so now this gives me a new operator on that subspace, because it can, like, the unitary conserve energy. So I can pick out an energy window.
Yeah, but it depends on
There are two things going on. One is you might have a Hamiltonian, which you're trying to evolve. That gives you an evolution. Another thing is in diagnosing what the complexity is. That's another question. You introduce a gate set which doesn't necessarily have anything to do with that Hamiltonian, and you just count up how many gates you absolutely need to get there. They're two different things. The circuit that you build to diagnose the complexity is not not necessarily an approximation to the time evolution, but I'm not sure what you were asking. I just point that out.
Sorry, what do you mean it's not an approximation to the time evolution? I thought if you take like some sequence of gates, you can try to approximate.
Yeah, but it's not that like
right?
each time step corresponds to one gate.
Yeah.
No, it's not only that. It's not only that. If the time is like so, supposing the time is very long, this is some chaotic Hamiltonian. But if you wait long enough, you'll have an extremely long time here. And if you were to think of this Hamiltonian evolution as a series of gates, you would have a very, very long series of gates. But there's a theorem which says you will eventually come back very, very close to the original state. If you come back to the original state, then
Well,
the relative
close in
complexity
this
is
measure,
zero.
close in complexity, or close in this.
Let's even say close in a product, which is an even stronger thing.
You're talking about Poincare recurrence.
Poincare recurrences. Quantum Poincare recurrences, eventually you will come back to a state which is arbitrarily close in both the, in the ordinary inner product sense. Right? And
Also in the complexity.
also in the complexity sense. And you'll certainly want to say that the complexity of that state, of that final state, is small. So there's not any necessary connection between, or direct connection between, let's say we approximate this by a product of gates. I'll tell you how we do that. If you build your circuit by a series of identical small circuits, you can think of the small circuits here as finite small time evolutions, just building up by multiplying the same thing over and over. That's what e to the IHT does. It multiplies the same thing over and over. So an approximate concept of a Hamiltonian evolution might just be multiplying the same short circuit. The same short circuit means, you know, a relatively small number of gates. Just keep multiplying it, multiplying it, multiplying it. That would be some kind of approximation to the time evolution, but it is not necessarily, and counting up this number of gates is not necessarily counting the complexity, because there might be short circuits. There might be shortcuts. We're going to talk about those. Okay, so, good. Some other notions. What is a super selection? What's the idea of a super selection sector? A super selection sector, you really mean states, a collection of states. For example, supposing your state space divided up into two kinds of states. And it was simply very, very difficult or impossible to make transitions between these. That's what you mean by super selection sector. I'll give you an example in a moment. But a good measure of what the idea of a super selection sector is to say, to go from one to the other requires an infinite complexity. How can that happen? Well, I'll give you an example. Supposing we're talking about a ferromagnet, even an Ising ferromagnet.
Should I always think of each super selection sector corresponding to some sort of conserved charge, basically?
Not
That's why
necessarily.
one to another.
You can always construct a conserved charge, but just by saying there's a number for one of them and a number for the other.
Yeah.
And since you never go from one to the other, it's conserved. Okay, but let's take the Ising model. Ising model all spins up. Let's suppose we have an infinite chain. If we have an infinite chain, then compare that with all spins down.
Right.
Or we have a ferromagnet in which we rotate the spins by a finite angle, all of them. The number of gates that it takes to go from here to here is infinite, just because there's an infinite number of them. And so we would say that for a ferromagnet, magnetization in different directions for an infinite ferromagnet is a super selection sector. What are the kind of states that you can interfere? You can interfere, for example, just flip one spin over and interfere that with no spins over. You'll rotate a finite number of spins by angles and so forth to make spin waves or whatever. And those states typically have a finite relative complexity to the ground state.
So they would be all in the same super selection sector.
Right, they're in the same super selection sector. And of course now you can think of approximate notion of super selection sectors. If the relative complexity of all states in here is very large compared to all states in here, then you'll say approximately for your laboratory purposes, they may define super selection sectors. There's another set of words that, similar idea. People talk about code subspaces. In particular, recently, due to work of various people that we know quite well, we have been thinking about ADS CFT. The bulk states in ADS are defined within a super selection set, or within a code subspace. Don't worry about what it means if you don't know. We'll come to it. But it means basically the same thing. Yeah.
Sorry. How about phases?
Say it again.
So people define different phases of matter when you cannot go by a set of local unitaries from one to another. So this is it related to your complexity?
So how do you do this?
I mean, when you have different phases of matter.
Yeah.
So this defined like you cannot go from one to another by a finite set of gates.
That's I would call those super selection sectors.
So, approximately.
Or for a finite sample, it's approximately.
I'm just saying those definitions very well match basically a gate definition, right? Because
Yeah, they do or don't.
they do.
Yeah.
So you're saying in ABCFT, the super selection sectors is because the overlap of two things that are distinguishable in the bulk are suppressed by one over n?
Sometimes, things like that, or even worse. Another example of superselection with sectors is simply all of the states in one quantum field theory, if you just change a coupling constant a little bit, because you change the vacuum everywhere, it would take an infinite number of gates to get back, even the tiniest change in a coupling constant, because the system, if the system is infinitely big, will take an infinite complexity to go from one to the other. And sometimes, even if the system is finite, because there's an infinite number of ultraviolet degrees of freedom, in most field theories, just a tiny change in a coupling constant will make all states of one field theory, all finite energy states of one field theory, simply orthogonal to all others, and would take an infinite number of gates to go from one to the other. So these are standard ideas, but they can be well expressed in terms of the notion of complexity. In choosing a gate set, you could just choose two qubit gates, but you could choose 2 qubit gates and 3 qubit gates, for example. And they would have different definitions of complexity. Now, what the connection between them is an interesting thing. Fortunately, they scale the same way with the size of the system and with the length of time, and then they're really not very different, but we'll come to that.
Can you think about adding these gates as a kind of correction to something?
I don't know, what are you thinking of?
I don't know, it's just like in field theory, you have, if you start with, say, 3 and 4 point couplings, loops will give you higher point couplings.
Yeah.
I'm wondering if you can think of something similar happening here, as you having like effective 3 gate couplings, or 3 qubit
No,
gates.
but that's a phenomenon of effective Lagrangian. He's talking about an exact quantum system that you literally have operators at
But
space.
it also relates for normalization too. If you take just two qubits and then you coarse grain it, you effectively have 3 qubits now. So
Right. Okay, so that's an important idea that if I allowed 3 qubit gates in my gate set, you can always make a 3 qubit gate, at least to an epsilon approximation. You can always make it by 2 qubit gates. And typically what that means is, at least if you're not worried about too short of time intervals, 1 gate, 2 gates, that the 2 definitions of complexity will not be the same, but they'll be pretty much related by a multiplicative constant. By a multiplicative constant, the multiplicative constant will be expected to be universal, which tells you something that probably the notion of complexity, unless we finally figure out what's the right definition or whatever, is probably ambiguous up to a multiplicative constant. And that's okay. But with any definition of the type I've given, relative complexity is a metric. The relative complexity between 2 states is a metric. So let's just go through the definitions of metric. Incidentally, for your own entertainment, you might try this out for the definition of metric that I gave you in a classical mechanics system. 0 complexity, 0 relative complexity for 2 points on phase space which are the same, and relative complexity 1 for any other 2. It's also a metric, a stupid metric. Definition of a metric. Well, the first criterion is the distance should always be greater than or equal to 0 for a metric. We're not talking now about Minkowski metric, we're talking about properly defined metric. All right, the relative complexity of any 2 states is always greater than or equal to 0. There's no such thing as a negative complexity. Furthermore, next element of the definition of metric, the distance between A and B is 0 if and only if A is equal to B. Okay? If you have 2 different states, there's no way to get to one from the other with 0 gates, obviously. 0 gates will always bring you back. So yes, the relative complexity of A and B is 0 if and only if A is equal to B. Next, the definition of a metric is symmetric. Distance between A and B is the same as the distance between B and A. As long as you include in your gate set, if you include a gate, if you include the inverse gate, then CAB will be, I'll call it C for complexity. CAB is the same as CBA. And the last one is the triangle inequality. let's write it down and then just check that it's true. This one's actually a little bit interesting. It says that complexity, well, we could write distance per Hallway complexity. CAC is less than or equal to CAB plus CBC. Okay, so how do we check this? Supposing we had a circuit, let's say it's the minimal circuit, which takes you from A to B. So here's a circuit that takes you from A to B. And now we have another circuit that takes you from B to C. All we have to do is put these two circuits together, match them up over here, and we have a circuit that takes you from A to C, and the number of gates that it has in it is equal to the sum of the two. But on the other hand, supposing there was a gate over here that just happened to be the inverse gate of this one. Then when we combine this circuit with this circuit, we can cancel these out. And you will have fewer gates. So you can have less than, but you cannot have this be greater than this, because you can always use the defining circuit for A to B and the defining circuit of C to B to give you a circuit from A to C. So it's a properly, for any gate set, it's a well-defined metric. There are ambiguities. One ambiguity is to change your definition of the allowed gate set. Another thing you could do is to weigh gates. For example, you can include 1-body gates, 2-body gates, 3-qubit gates, 4-qubit gates, all the ways up to n, but with a weighing factor, saying that 3-qubit gates are more complex than 2-qubit gates. 4-qubit gates are even more complex. So you can play games like that and introduce a wide class of definitions. And as I said, by a theorem someday to be proved by my friend Aronson, at least when the circuits are not too small, they're all multiplicatively related. Okay. Now, I just made that up. I think you who have listened to me before know I make up things.
Yeah.
But I also tell you when I make up things.
Sometimes.
At least when I tell you.
Yes.
Okay.
An order of one fraction.
Yeah.
I always tell you. Oh, sometimes I may not know that I made them up.
No, yeah. Eventually you're gonna find out, yeah.
Okay. Eventually you'll find out.
Yeah.
All right. Now, yeah. Oh, you're not in the sun, okay. Yes.
So maybe I'm confused, but is it a problem that finite time evolution by like a very simple Hamiltonian can give you an operator of infinite complexity?
Can give you
an operator of infinite complexity. I mean, just take sigma x on every site in your ferromagnet and evolve for like pi/2 time so that you flip all the spins.
for an infinite system. You're asking about an infinite system
Yes.
now. If the system is finite, the answer is no. But if the system is infinite, yes.
So even like, so by this definition, like even a very simple Hamiltonian can move.
It's a
states
simple
really
Hamiltonian, but, right, it is a simple Hamiltonian. It's simple and it's not simple. It involves all the qubits. So, okay, so let's think, how would you do it? How would you flip, in a laboratory, how would you flip all of the spins? You put it in a magnetic field, okay? But you have to put it in a magnetic field of infinite extent. So the difficulty here has to do with having the magnetic field have infinite extent. If you only put it in a field of a magnetic field of finite extent, you only flip a finite number of spins. So in this particular case, the infinity and the complexity is coming from the volumes. And
So I guess my question was, if you subtract off, like, if you say, okay, it has to grow faster than, like, the complexity has to grow faster than polynomially in system size, will you be able to differentiate chaotic Hamiltonians from not chaotic Hamiltonians in this way? So you could say,
okay.
like, okay.
Well, let's get it right now. We're saying we have a Hamiltonian, and we're going to ask what? We're going to ask what the maximal complexity it ever generates when it acts on something particular?
Sure, in finite time.
What's that?
In maybe some finite time, for example.
That
Less than
will
one for
distinguish
less
different
than one.
Hamiltonians. Yeah. Some Hamiltonians, for example, no matter how much time you involve, will not generate very much complexity. They tend to be the integrable Hamiltonians. They just never generate very much complexity.
But you wouldn't call, so you wouldn't call sigma x on every set integrable by this definition in an infinite system.
That's, they picked an infinite system. Supposing we pick a finite system. Yeah, I would call that integrable, but let's take a finite system. Integrable systems do not, in any case, generate very large complexity. They tend to make periodic oscillations and things. They don't generate large complexity. The things that generate large complexity are chaotic Hamiltonians. This picture here, I drew a picture for you that looked like this, like that. Integrable systems tend not to do that, and they just tend to oscillate around something. But this is, you're asking an important question about maximal complexity. But not maximal complexity given a Hamiltonian, but just what is the maximal complexity for n qubits that is possible altogether? Is there a maximal complexity? So let me come back, let's start with a classical example. In the classical example, which is the same as just looking at the states which are in the computational basis. Everybody is either a 0 or 1. And if I were to ask, what's the maximum number of bits that you have to flip to go from A to B? The answer would be n. The maximal state complexity, if we were, for example, to say that A is our simple state, and we take any other state for B, then the maximal complexity of any other state relative to A would be n. It can't be bigger than n, okay, which is relatively small. Yeah.
Shouldn't we also be thinking of superposition of states? I mean, that's
Yeah. I said in the classical case.
Yeah, okay, so.
In the classical
Okay,
case.
didn't
Right. All right. From where does this large complexity come from in quantum mechanics? This was originally Feynman's observation. I don't know why it took so long. I don't know why people didn't say it much earlier. If you look at a classical state of, for example, this kind of system, and when I say state, I don't mean probability. Oh, let me say one thing. I will use the term state in classical physics to mean a distinct configuration or a point in phase space. I will never mean a probability distribution. In quantum mechanics by state, I will mean pure state and not mixed state. Okay, I hate thinking of probability distributions of states. And the reason is because probability distributions are subjective. What's the probability that my wallet has $50 in it? I ask Jonathan, he tells me 10%. Tell me, I tell you it's 0%. So that, I mean,
All right.
probability distributions are in the mind of the,
Yes.
At least classical probability.
Right.
Because when I say state, I mean it, I mean configuration.
Observer dependent.
Okay, so the maximum state complexity that you can have for a classical system is basically n.
Right.
It can't be bigger than that. What about quantum mechanics? Well, first let me remind you, when I say a classical state here, I mean a collection of n binary digits. N binary digits defines a class. What about a quantum state? A quantum state means all possible superpositions of these. So it's a sum from 1 to 2 to the n, there are 2 to the n such states, of amplitudes, I'll call them alpha I, where I represents one of the computational states, times I. Let's take the very simplest situation, or the very simplest approximation. Let's suppose the alphas are all either 0 or 1.
Okay.
This is much less than the full richness of the set. How many parameters How many binary digits does it take to describe a state? 2 to the n. Okay? So a quantum state is a much richer thing, or the ability to describe it is much harder than a classical state by a full exponential. That's why the capacity for quantum states or quantum systems to be much more complex, that's the reason that quantum states can be much more complex. And how complex? This is a theorem, it's a counting theorem, which I'm not going to prove. I don't even think I remember how to prove it. I read the theorem and I knew it one time. But again, we start with circuits. And we ask, what's the maximal possible complexity that you can generate, not by a particular, but by any circuit? Any circuit built, let's say, out of 2 qubit gates. And the answer is the same 2 to the n. It's of order 2 to the n. There's a prefactor in front of it, and the prefactor is a thing which might depend on the gate complexity, on the gate set, and so forth. So the level of ambiguity is in the prefactor. And what is true then is the absolute maximum complexity independent of all definitions, even epsilons, is of order 2 to the n, C max, times a prefactor which can depend on epsilon, times it can depend on the gate set. But C max is 2 to the n for relative state complexity, and 4 to the n for, this is for states, and this is for unitary operators.
Sorry, Lenny, can I ask a question about this prefactor?
Yeah.
So
I'm not sure I know the answer.
I'm jumping the gun a little bit,
Yeah.
but in complexity equals action, you guys try to interpret the prefactor.
Right.
You see what my question is?
Yeah, no, I do. No, but I think we were also quite emphatic that the prefactor at present really doesn't have any well-defined meaning. It was a speculation that there exists a best definition which might agree with that prefactor.
Okay.
Yeah. So that was neither here nor there.
Does 4 n come from just the fact that I can construct unitaries like in a basis of outer products of states?
Yeah.
It's just that.
Yeah. Yeah, small parameters are operated because of the connect states.
Okay.
So in some senses, ambiguity kind of implies that we should really think of like log of the complexity as being on par with any other thermodynamic quantity.
Well, that's an interesting question. I don't think so, but we'll come to this. We will come to that.
Okay, I'll wait.
I think there's a sense in which complexity behaves more like entropy than log of the complexity. But not in the usual sense. Not in the usual sense.
Okay, I'll wait.
So hold on to that. Hold on to that thought.
Would there be?
There may be some sense in which log of the complexity does. I never saw
It has the same ambiguity in the sense that if you look at the leading large n behavior of thermodynamic quantities, that's well defined. Leading large n behavior of log of complexity is well defined, and then the additive.
The log of the maximal complexity is that's right. So,
But even during the growth period too, the leading large n behavior of the log of the complexity is something that's clear, but the multiplicative constant.
we're going to talk about
Okay.
that. We're going to talk about that. That's I think what you're saying is wrong, but for non-trivial, non-obvious reasons.
Okay.
Okay. Good. All right. To get some intuition. This is for the purpose of getting some intuition. Later on, it will become a main theme, which is more for quantitative reasons. But for the moment, let me imagine the space of states. The space of states, or the space of unitaries, the space of unitaries. The space of what is the space of unitary operators for n qubits? Special unit, we don't care about overall phases. It's S, U, what? In? To the n. SU, it's a huge group, SU2 to the n. There's a space of unitary operators on any qubits.
Because you go back in that basis.
The dimension of the Hilbert space is 2 to the n, not n. Good, so this is this is, as I said, a big space. Let's draw it. It's a homogeneous space, it's not a sphere, except in one case.
Block sphere.
Hmm?
N=1.
Yeah. Yeah. Yeah.
Yeah, N equals 1.
Which is 2 units.
Why didn't you have the SU2
I
out?
don't know, maybe there are other cases. Is there any case where SU2 to the end is a?
No, I think the generator, you run it, the generator takes
Yeah,
it.
no.
No, it's just,
Right, okay, but it's a homogeneous space, which means every point is the same as every other point. So I'll draw it as a sphere since I have no idea how to draw it. Well, it can be embedded in an orthogonal group.
yeah, sure, just the point is it won't be the same.
No. And let's put the unit operator over here. And let's say some unitary operator over here. And think of the circuit which takes you over. Now, I want to put a metric on the space. What metric? Well, I could put the standard inner product metric. There's an inner product metric also for unitary operators, incidentally. I could put the standard metric on here, and that would be fine, but then the maximum distance between any unitary and any other unitary would again be the silly pi/2. On the other hand, if I use complexity distance, and the complexity distance between, what would be the relative complexity between two unitaries? Suppose I have two unitaries, I don't want to define the absolute complexity as the distance or the complexity relative to the unit operator. Supposing I had U and V, how would I define the relative complexity of U and V? It would be the absolute complexity of U V dagger.
Right.
How many, yeah, okay.
Yeah.
Right, you want to write that V is equal to G times U. And so we can write that G is equal to U dagger. The number of gates here would be the absolute complexity. So there's a notion of relative complexity for unitaries as well as for states.
What am I using for a norm?
Norm or?
Norm of the SU2.
These are unitary operators, no need to
Okay.
normalize them. But they
No,
are-
I meant like,
Oh.
I meant norm like on this function space. Like, yeah, they're just determinate one. Usually like the
Yeah.
supremum.
Yeah, okay, and to go between any two unitaries, in particular to go from the identity to U, there's some minimal gate set, minimal circuit. Let's think of that as a sequence of steps. And since this is the minimum sequence of steps, there's a sense in which the minimal circuits are geodesics in the space. I'm allowing the space now to have a metric on it, which is the complexity metric. We'll take the distance on the space.
That's by definition, right? Because you
For the
define
moment, yeah.
the
Well, there are two metrics. One of them is the inner product metric, okay? Then the maximal distance to pi/2. But if I use the relative complexity metric, as we defined it, then the subject to some constraints, the trajectories here which minimize the number of gates to get from here to here can be thought of as geodesics. We'll work on that theme. There is a geometry of complexity that goes through Michael Nielsen and generalizations of it, which does actually think of complexity as geodesic distance on a space. But I only want to think about that now as a kind of mnemonic for what's going on and draw some pictures.
Would tensor products between different systems correspond to like tensoring the groups? Like if I had one set of n qubits and another set of n qubits and then I wanted to, so then I would have like SU2 to the n tensor product. So with that, you could view that as like stitching spheres together, I would think, or,
It's a product space.
yeah. Not stitching, I mean
It's
like,
not stitching.
Yeah.
no, I mean like fibering, yeah, fibering.
Or something like that.
Sticking two of them together, however you want to define sticking two of them.
No, I wanted every single point on one of the spheres to be another sphere.
Product space is the word.
Yeah.
That's a product space.
Yes, yes,
Or,
The,
so, yeah.
yes,
the natural product when they're in the manifolds.
we don't, continue,
Okay.
The thing you just said.
Yeah.
yeah.
Okay, so we have a concept, even if very crude now, of the notion that relative complexity between two unitary operators, for example, can be thought of as the distance, not only the distance of a geodesic, but the distance of the shortest geodesic between two points. There may be more than one geodesic between two points.
Go around the normal.
This is what I want to examine now for a minute, this idea of shortcuts. All right, so let me imagine space now. I'm going to draw it just as a blackboard, just to indicate what's going on here, what a shortcut means. And let's imagine that in this space here, here's what the space looks like. It looks like a flat plane approximately, and has a great big bump in it. Okay, there's a great big bump in it. And so it makes it hard for the short geodesics will wind up going around the bump. So let's, space on here's the bump. There's the bump, and let's start over here. This could be the unit operator over here. And take some Hamiltonian, h, and allow it to evolve so that we construct u equals h e to the I minus I h t. This will define a trajectory for a given Hamiltonian. It will define a trajectory, and that trajectory will be a geodesic. That I'm not going to try to prove. Okay? This will be a geodesic. I just realized that it requires a proof to show that, but I only just realized it, so I can provide proof. We'll do that. But, all right, so we start here, and let's say we go to here. We avoid the top hill here. There's a geodesic which goes from there to there. And in particular, it's the geodesic e to the minus I h t. And of course, time ticks along here. And so there's a flow along here. But in particular, we fix some time. And that geodesic is a geodesic. There's another one. At least one more, but if there are lots of hills and valleys, there may be many. But in particular, there's the one that goes around here.
Yeah.
Okay, now, this one is clearly shorter, right? And in fact, if our time interval here was short, then this geodesic would be obviously much smaller than this geodesic. And so we would say the shortest geodesic defining the complexity would be the one that was actually generated by the Hamiltonian itself. But let's suppose now, I'm going to draw another picture just so we have this one loose on blackboard. Wish I had some colors.
Get some colored box.
Don't worry, don't worry. Oh, yeah, you want to get some?
Like just said, all right.
Can you actually have hills like this though? Because I thought you said that. Can you have bumps like this? Because
Yeah,
I thought you said that it was the same.
The space defined by the complexity metric is not a homogeneous space. It's a complicated space. It does have structures in it. It has complicated structures in it.
Do you have an idea what this space looks like? Like if I write the metric on this SU to the n and radial slicing, like dr squared plus something.
Something like that, yeah.
Can you say anything about the warp factor for the level surfaces, or is it some limit where it's
The level surfaces for the complexity metric.
Yeah.
This is a very important concept, but not too much known. We're going to talk about this space in detail. Mm-hmm. It's a very, very interesting space, about which very little is known.
Okay.
It is what is called a left invariant metric on group space, and it's a subject of intense investigation by mathematicians, and almost nothing is known. It's a hard subject. We're gonna now there's a difference between what mathematicians know and what physicists know, because the word know is different. It all depends on what you know. Not they know, but T-N-O-W. Okay. So now let's suppose that this geodesic if extended, and by the white geodesic here, let's draw this one's green. So the green geodesic is not generated by this H. It just happens to be another geodesic which connects this point and this point. It just is. Okay, now let's go a little bit further in time and go around to about here. The original geodesic, which looked like this, maybe went around here. Let's draw it down. It went around and connected over here. It doesn't connect to this point. This is a little further on. But that geodesic can be deformed until it does get to that point. Okay? So it's a new one. It's not this one is always the same geodesic, generated by H. This one just follows this point as it goes along. At some point, this geodesic may get as long as that geodesic. You know, in this picture it would. There would come a point where this one became the same length as that. If you take a lot of geodesics, a whole family of geodesics coming out of here, and you plot the points at which shorter geodesics emerge, that's called a cut locus. The mathematical term for that is the cut locus, and this would be called a cut point, where the shortest geodesic jumps from the defining geodesic associated with the Hamiltonian in this case to a new geodesic. You go past there, so we keep going past there. Let's stop this one now because we come to here. Now the shortest geodesic is very distinctly the one that went this way. Well, maybe not distinct, yeah, it will become. Once you pass the cut locus, there's a new geodesic. All right, so which is the definition of complexity? Is it the one generated by the Hamiltonian? There's a term that is used in various contexts. It's called local optimization. Local optimization, this could be a geodesic is an optimization of a distance. And it's locally optimum in the sense that if you move it locally, it's a minimum. But it's not a global optimum. Okay? So the question is, what do I mean by complexity? And by the definition I gave, it's the global right. Okay, are we sure we want to be talking about the global one? So let me give you an example that makes it kind of clear that we do want to be talking about the global one. Let's suppose, for example, that we run this thing for a very long time. We run it for a long enough time, and it will wander around hugely in the space before executing a quantum recurrence. It'll come very close to here. You don't want the complexity of this unitary over here to be hugely big, because you can go from here to here easily. So the answer is, if you want a reasonable definition of complexity that's independent of the path that you take to get to the state, you just want to know the complexity of the state, nothing about the path that you happen to take, then we want the global optimization. Okay, so we have the idea of shortcuts. The shortcut is going the other way. Complexity is associated with the shortest possible path. And that makes it a function not of the path, but of the state itself, or the unitary itself. It's a function of the unitary and not the path that you took to get to it. That's yours.
Yeah.
Where's mine? Oh, here it is. If you hadn't told me, I would have written I would have given a class on
Zeta function.
Zeta. All right. We'll go on for another 15 minutes. The traditional subject of complexity is mostly about organizing questions, problems. The problem could be getting to a particular unitary from unit operator. It could be solving a theorem. It could be walking from the North Pole to the South Pole. It could be all kinds of things. It could be evolving a human being from a worm. The complexity of a human being could be defined as the minimum number of mutations that you need to get from a right. The complexity of a theorem could be starting with the postulates. What is the minimum number of logical steps that you need to get to the theorem? So always this same idea. And this traditional subject is organized around complexity classes. Complexity classes are broad qualitative classes such as P and NP and X. P is the class of problems that can be solved in power law times the class of problems for an n bits, for example, which can be solved in polynomial time. NP is something else. It's not non-polynomial, but it's something else. But X would be the things that can only be computed in exponential time, and it lumps questions into these broad complexity classes. The new subject, which is gaining some traction now, I mean, some of my friends who do complexity theory are getting extremely interested in it now, is a very, very different kind of question. It's a question of the dynamics of complexity and how complexity varies with time. In particular, you could imagine a quantum computer. Let's program that quantum computer to execute a series of steps. These steps could be totally meaningless and have no particular purpose in mind. It could be mindless computation, just the computer is running. And we could ask, how does the complexity of the state of the computer evolve with time? This is a very different question that, and it has only come up, to my knowledge, it was never really asked very thoroughly until we started thinking about complexity in the context of black holes. It's gained some traction. People like Aronson are very interested in it, other groups of people. So the question is, what is known about the limits on how complexity grows? And the answer again is very little is known. If by known we mean, theorem known, very little. There are some conjectures, and I will tell you what is conjecture, and it's almost everything. But the conjectures are things which have some substance to them. Typically, okay. First statement. You can understand this first statement again. I don't think it's a theorem. Supposing you have some circuit which you're following in time and asking how the complexity builds up. You might think, well, maybe it's just the number of gates in the circuit. But wait a minute, there's shortcuts. Okay. The typical answer is that for some length of time, it is just the number of gates. It's basically the insight that a geodesic, this is a theorem about Riemannian geometries, that the first cut locus occurs after a finite distance along the geodesic. So there's at least a finite time that you get that the geodesic generated by e to the iht in this context here, the length of it, so to speak, is the minimal length of any geodesic for some length of time. The way the complexity people always tell me, the way you say this is that the most efficient way to generate a state is from the circuit which actually generated it. Whatever actually generated it will be the most efficient way to generate it for some length of time. It may be a very small length, it might be a very long length of time. And the basic hypothesis, there is a theorem about this, but it doesn't say, it's not strong enough to say what I'm going to conjecture. Basically, that generically, the first cut locus doesn't happen until you reach something exponential in the complexity, exponential complexity. In other words, the complexity increases linearly with time, which is basically, it can't increase faster than linearly with time. Why not? Because if you just take your series of gates, the complexity is not going to be bigger than the series of gates, assuming the gates are laid down uniformly in time. Assuming the gates are laid down uniformly in time, then the complexity can't grow faster can't be bigger than the number of gates that you use to generate the circuit. So it's bounded above by a linear growth. The assumption I will make, and we can question it, and it's fair to question, and it would mean something for gravity if it weren't true. It means something for gravity even if it is true, is that the complexity increases at the fastest possible rate until it hits the maximum possible. It can't be bigger. Remember, maximal complexity is either 4 to the n or 2 to the n, depending on whether we're talking about states or unitary operators. That it just increases linearly until you hit the maximum. There is an analog in statistical mechanics, and it is the statement that entropy increases linearly until you hit equilibrium, until you get the equilibrium, which is the maximal for a given energy, for example. There is a quantity in highly mathematical chaos theory. What is it called? It's called the Shmulevitz-Gonsorovich entropy. No. The Kolmogorov-Sinai entropy, right? The Kolmogorov-Sinai entropy, which is basically just the rate of increase. It says the entropy increases linearly. I'm not even going to tell you what it is until you get basically to equilibrium. Okay. The entropy is what increases linearly. The complexity, we're going to argue, behaves like the entropy. It increases linearly until it can't decrease anymore because it comes to some kind of equilibrium. Now, the maximal entropy, why does the system, what does the system do, statistical mechanics system? What states are the most numerous? Let's say for a given energy. It's the ones that you characterize as having the maximum entropy. Right. So what happens is the system will, wherever it is, it will tend, the entropy will tend to increase because there are just more states of larger entropy. That doesn't mean it can't decrease, it just means it's most likely to increase because there are just so many more states. And it will do that until it gets to the largest entropy, possible entropy. And then it will wander around in this enormous number of states of high entropy until by accident, it'll, by fluctuation, a large fluctuation will occur and a recurrence will happen. And these are very infrequent on very, very long time scales in statistical mechanics. Complexity appears to be something like entropy. The bigger the complexity, the more configurations there are. This is certainly known, that if you ask what is the number of states or the number of unitaries with a given complexity, it grows exponentially with the complexity. We can talk about this and we can try to see that that's true. As the complexity gets bigger and bigger, the number of states or the number of unitaries with that complexity grows fast. So what does it mean? It means if you start your computer with some complexity which is not near the maximum, most likely, either going forward or backward, but let's say going forward, the complexity will increase just because there are so many more configurations of more complexity. It's kind of second law. It's not a second law of thermodynamics, it's a second law of complexity. Right. But eventually, just like entropy, there is a maximum. It's much bigger than the maximum for a classical, than the entropy, the maximum entropy. So eventually it will hit the maximum. When it hits the maximum, it will wander around in these states of very high complexity. There are just so many of them that the system will wander around in high complexity states until it executes some kind of fluctuation and unwinds the complexity again. But that's on possibly long time scales. So I think it's and it increases linearly, just like the entropy does. So I think it's the complexity which behaves like an entropy, but not like the true entropy of the system. It's quite different. It's a different quantity. Different quantity, and it's typically much, much bigger than the entropy.
Would there be analog like a partition function or Boltzmann distribution?
Yeah, I don't think so. But what's the maximum entropy of a system of n qubits? N log 2.
Yeah.
Right. What's the maximum complexity? 2 to the n. It's much, much bigger. If complexity increases linearly, it means it will increase for an exponential amount of time, whereas the entropy of the system coming to thermal equilibrium will only increase for a time of a much more modest time. So complexity is not entropy; it's a different quantity. Its maximum is very, very much bigger, exponentially bigger, but in some way, and I'll try to quantify in what way I mean that. Imagine we take a generic system, a generic quantum computer, or a generic circuit like this, with some set of rules. For example, it could just be a random circuit. It could be a circuit which just repeats the same basic unit over and over again. Then, supposing we plot complexity versus time, it will increase linearly, at least for a while. So it will increase linearly for a while. Up here is the maximum complexity, that's 2 to the n. And by hypothesis, interesting, by hypothesis, it grows as fast as it can, which means linearly, until it reaches the maximum. And this may be a cartoon of something which is possibly more complicated. Will it ever hit shortcuts? Well, yes, it hits shortcuts up here. When it gets up here, it must be because, why doesn't it continue to increase? It must be because it's constantly hitting shortcuts. If it tries to increase a little more, apparently it will hit a shortcut because it can't increase anymore. If you wait a doubly exponential, a very much longer time, this time scale here is e to the n, e to the number of qubits, or exponential. Why? Because it's increasing linearly with a finite rate. The rate is not very large, and it gets up to 2 to the n, so it increases for a very long time. And then eventually, just like entropy, it will come back down. There's just no, it will come back down. This is a theorem, this can be proved. It'll come back down, let's say this is a long, long time has evolved, and then it'll come back down and go back up. That's a recurrence. That's quantum recurrence. And the most likely thing to happen during a quantum recurrence, well, a quantum recurrence is totally unlikely. But let's constrain it by saying this recurrence actually brought you down to very low complexity.
Okay.
We have to wait. This time scale, incidentally, is e. If this is e to the n, this is e to the e to the n. This takes a very long time. But it's basically a symmetric kind of thing. Let's suppose we know that we got to here. We ask, what's the most probable thing that we see if we run it backward? And what's the most probable thing that we see if we run it forward? Well, by the time symmetry of the evolution of quantum mechanics, the most likely thing you see this way will be the reflection of the most likely thing you see this way. And so the most likely thing that will get you down to the bottom here will be a symmetric thing like that. Same thing for entropy. Same thing for entropy. Poincare recurrences tend to be, they typically are symmetric like that. Okay, how would I compare this with the growth of entropy for, let's say, a classical system of n degrees of freedom. Classical system of n degrees of freedom, the maximum entropy is order n. The time that it takes, it also increases linearly, so the time that it takes will be polynomial n. It will execute classical recurrences on a time scale of order e to the n, not equal to n. And so qualitatively, the evolution of complexity looks like the evolution of entropy, but not an entropy of a system of n degrees of freedom, but an entropy of a system with exponentially many degrees of freedom. Qualitatively, that's the way complexity would be expected to increase. The whole thing being blown up exponentially compared to the way thermodynamics works.
It's almost as if you, instead of having entropy, statistical mechanics of degrees of freedom, you have thermodynamics, statistical mechanics of the basis of state, of the actual basis of qubit. Instead, it's almost as if instead of having a statistical mechanics of the number of degrees of freedom of the system, you have a statistical mechanics for the number of basis states. Yes.
Not number of basis states.
And the number of states.
Number of states,
sorry.
period.
Number of states.
The number of states, remember, the number of states.
Yeah,
is
the
vastly
total
bigger, right?
number of states. That's
Right,
right.
number of states.
You basically list out all
the
states. and then
statistical
you use
mechanics,
states
those
of-
phase space
Yeah.
is actually the space of states, right?
Right.
The manifold of states.
Right.
Yeah.
But if we try and think of complexity as a resource, though, then again, it'll probably be more like the log of the complexity that we could compare to other thermodynamic quantities.
I don't think so. I think it's the
Because, I mean, but we would never, in a finite system with finite energy, we could have this exponentially large complexity, but we won't get the exponentially large energy out of it. At the most, we could get a log of the complexity energy or decrease in entropy if we're...
The question is whether entropy is the right thing to compare, whether energy is the right thing to compare with the thermodynamics of... I won't answer that now. We'll talk about that. We'll talk about whether there is statistical mechanics of complexity, not thermodynamics of it.
Yeah, I'm just trying to think about how to use it as a resource to do other things.
Yeah, think of entropy for a minute. You don't use entropy as a resource, you use negentropy.
Yeah, use negative entropy, sure.
Right.
But,
Yeah.
like, is there anything that prevents you, one, from just simply constructing the statistical mechanics of the states and then seeing if it follows these complexity conjectures? I mean, I guess you don't have a Hamiltonian or a partition.
Is there anything that prevents it? Yeah, just the very, very complicated nature of this space.
Yeah.
Of this complexity space, which is a horrendously complicated thing.
All you need is 2 to the n experimenters and 2 to the n
No,
labs.
yeah.
No, I think it's a good question, and if you compare the difficulty and dimension of the space with the number of people who've actually tried to understand it, it's got a Maltz ratio of.
Yeah, right.
Yeah.
It just seems to be screaming out that if I had some kind of Hamiltonian, or not Hamiltonian, but something that would involve, that this is like, it's a statistical mechanic, just that you have more stuff.
Well, we're going to talk about that. Yeah, we're going to talk about that. That is a theme that is interesting.
If you knew the distribution of complexity in the Hilbert space, like somehow like take all the operators and then like exponentiate them and then figure out where they land and get a distribution of complexity density.
Right.
Here's what is known with pretty good confidence, I think, that the number of operators with complexity C, number of unitary operators or the number of states grows exponentially with C. That makes C more like entropy. Like C is like the logarithm of the volume of what is going to stand in for phase space. So it's it's a single exponential, it's not double exponential. But these are good questions, and we should come back to them. Next time we will go to black holes. Black holes and complexity, and compare what we've learned, in particular with this curve here, compare with what we know about evolution of black holes, and discuss to what extent it looks like complexity is a quantity that occurs in black hole physics. So we'll quit for now. Okay. Next week we have Ron, who will